Okay, so our next example in section 8.5 for our second video here is the Bessel function of order 0. So this is a function or is a family of functions with different orders, of course, that are very useful in physics and engineering. We won't do much here other than find its radius of convergence and interval of convergence, but it's a start, and probably later on you'll see this function used in solutions to physics problems. So this function is only expressed in terms of a power series, which is an interesting thing to note. We see that the center of this power series, despite all the complication in this, the center of this power series is 0, right? We don't have x minus any constant in there other than 0, right? X to the 2n is equal to x minus 0 to the 2n. So we identify the center as 0. And we're, curious as to where this thing converges. That's a useful thing to know essentially what the domain of this function is then, what x values this thing has a finite value for. Okay, so that is our task, and we use the usual method. We apply the limit or the ratio test, the limit of the absolute value of a subsequent term divided by the term before it. A sub n plus 1, everywhere there's an n, we replace it with n plus 1. That's happening here. Since there's an absolute value on the outside of this this expression, this ratio that we have here, I'm not even going to bother to put the -1 in here. It's just not going to matter. It's going to go away anyway with the absolute value. So it's essentially already canceled. Now we divide by a sub n, and that's essentially just this term on its own, again without the -1 factor, because the absolute value gets rid of that. So let's group the x's, or first things first, we're dividing by a fraction, so we'll multiply by the reciprocal of that fraction. Now we'll group the like terms. All the x's are grouped together. Exponential functions, 2 to powers of n, are grouped together. And then our factorial functions are grouped together as well. Okay, group like things because like things cancel. So working our way downward, this leaves us with an x squared here. 2 to the 2n over 2 to the 2n plus 2. Well, that's there's an extra factor of 2 squared that we can write away from this, and that leaves us with 1 over 2 squared after our cancellation here occurs. And then we've rewritten this a little bit more carefully. We've taken this whole fraction to a square, because the next thing we need to do is handle the factorials inside here. And when this cancels, it's just like the last problem we saw. We end up with a 1 over n plus 1, still quantity squared. Okay, now we have a look at what we end up with. This is 1 over n plus 1 squared. We could square this out if we want to. It's the only function, it's the only part of this expression that involves n still. And as n goes to infinity, this expression is driven to 0. These are constants with respect to n. So again, our limit of this ratio goes to 0. We impose our condition of convergence for the ratio test. In other words, we just write less than 1. And then we note that there's nothing to solve here. This is true no matter what. So this is true for all x values. So our radius of convergence is all real numbers. So r, again, is infinity. So typically, or in a lot of problems, when we're done here, we have some function of x, and we need to solve for the absolute value of x, or the absolute value of x minus some number to know what the radius is. We'll see that shortly in another example. But in this case, it's just a 0. This is always satisfied. So this is convergent for all real numbers. So our radius of convergence is infinity. Our interval of convergence is all real numbers, negative infinity to positive infinity. And that wraps this one up. So really, once we know the main technique here, it's just a matter of quite a bit of algebra to evaluate all this, to simplify all this, and then just a little bit of calculus, just a limit in the end. So let's see another example where we have a non-zero center. Okay, so we're given a power series centered around 3 because we have x minus 3. So a is equal to 3 in this case. Center is 3. So I'll write that off to the side. X minus a equals x minus 3, center A is equal to 3. Okay, positive 3. So we know we're centered at 3. Another way to know that we're centered at 3 is if we plug in 3 for x in this expression, we get a convergent series. We get all zeros added up. So that's the one place we know it's guaranteed to converge. Now to find other places it might converge, we use the same format as before. The ratio test, our n plus 1 term divided by our n term, and taking the reciprocal of the second fraction or the denominator fraction and multiplying. We'll then group like terms. The x minus 3 terms are grouped together here. We'll see a nice cancellation in this case. And then we've got 2n plus 1 over 2n plus 3. There's not much to do for cancellations here, but it will be an easy limit to handle. We'll see that in a moment. Now we've got x minus 3 after these n factors of x minus 3 canceled and only 1 in the numerator remained. So we've got that x minus 3 off to the right times this function of n. Now as n goes to infinity, 2n plus 1 over 2n plus 3, remember it's the ratio of the two lead terms because the degrees of these polynomials match. Both degrees are 1 and their lead coefficients are 2 and 2. So it's 2 over 2. So that limit goes to 1. And that's times x minus 3. Remember, x minus 3 has nothing to do with n. It's constant with respect to that limit. So all you focus on is functions of n, expressions with n in them. So this limit is equal to the absolute value of x minus 3. The only thing in here that survives that's not 1 is x minus 3. Now we impose the condition of convergence for the ratio test as less than 1. So now we know that the absolute, so this is this altogether, this tells us everything we need to know, this inequality right here. We have absolute value of x, its coefficient is 1, so we're perfectly happy with this. We don't have to work any further. We have x minus 3 less than 1. So what we pick up is that this coefficient's 1 inside absolute value, and it's less than 1. So our radius of convergence is then 1. Okay, that's our scale. That's how far we can move away from 3 is 1. So in other words, the distance that x can be from 3 has to be less than 1. So that's our radius of convergence. And r equals 1 in that case. Then we work our way down here to find our interval of convergence. And that's just a matter of solving our inequality that we've got. So remember that absolute value of x minus 3 is satisfied if x minus 3 is greater than -1 and it's less than 1. We solve this system of linear inequations. We solve this linear relation simultaneously. We add 3 to all 3 sides, and we have 2 must be between, or sorry, x must be between 2 and 4. So then our question is this. We have 2 comma 4. Do we have parentheses or brackets or one or the other or bracket parenthesis? What can we include either of these endpoints is now the question. So it's a step we haven't seen yet. It's pretty straightforward to follow through with it. And we'll see the details here. So we're checking the endpoints. So we'll first check the left endpoint. Is this a convergent series when x is equal to 2? Well, what do? You plug in x equals 2 to the original series all the way up here. So we have 2 minus 3 in our current series. And what this yields is a numeric series, right? There's no x in here anymore. We're just dealing with n, which is the typical numeric series. So we have -1 then to the nth power, but we also have another -1 times n. So these two things make -1 to the 2n. Well, that's always squaring -1, so that's always positive. So we always have a positive 1 in the numerator. The denominator didn't change much. 2n plus 1 just sort of came along for the ride. And we end up with a series that looks like 1 over 2n plus 1 summed up, right? If you use the limit comparison test, which you should, and carry out these details as a student, you should show that through the limit comparison test, comparing to the series term 1 over n, you should find that these two are linked through the limit comparison test. And then you note that this one is the harmonic series, or at least that is the term for the harmonic series. That's a divergent series. So you know that the given series here is also divergent. Okay, so when x equals 2, we have a divergent series. So we do not include 2. So this parenthesis here is appropriate. Now check at the other endpoint when x is 4. Do the same thing. Plug in 4 for x. We have 4 minus 3 in the numerator here. That's 1 to the n. And we have negative 1 to the n, right? Because 1 to the n is just 1. So that sort of cancels, or we just don't write it anymore. And we're left with just this first term in the numerator, negative 1 to the n. And that's over 2n plus 1. And now we're assessing this series right here, negative 1 to the n over 2n plus 1. So it's an alternating series, so let's use the alternating series test on it. The positive version of this, right? We ignore the alternating part, the negative parts, and we just take 1 over 2n plus 1, the positive part of this, and we check it. As n goes to infinity, this thing goes to 0. So that's the second condition. The first condition is that this thing needs to be decreasing. So I'll write this down. 1 over 2n plus 1 plus 1. So the a sub n plus, or b sub n plus 1 needs to be less than or equal to b sub n. And if we carry out the details of this, we'll find that this does in fact check out. What you do is multiply both sides by this denominator, both sides by this denominator, you'd get another inequality. Eventually you get an inequality that you know to be true for all n greater than or equal to 1. So this one's convergent by the alternating series test. Again, in both cases, the student should confirm the details of these tests. They're mostly done here, but you know, there are quite a few details to finish off and see. So be sure you can do those as good practice. Since we have a convergent series when x equals 4, then we can include 4 in this power series interval of convergence. In other words, we can include this 4 in the function f of x, which is equal to this power series. So in other words, 4 is in the domain of that function. So we want to think about these power series as if they are functions, because that is in fact how we're going to use them. And that's the main purpose of having such a thing, is that it is a function that we can work with. They're often solutions to differential equations, which are used to model tons of things in physics and engineering. And they're also very valuable for approximation. So that's it for power series. This is the most complicated situation in non-zero center, and then checking the endpoints to be sure that one or both or neither endpoint should be included. And the main theme is that we always use the ratio test. We always impose the condition of convergence for the ratio test, and then we interpret what that means for the radius and interval of convergence. So that's it for 8.5.